Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1796. The world, freshly reshaped by the scientific fervour of the Enlightenment and teetering on the brink of revolutionary upheaval, witnessed the publication of Pierre-Simon Laplace's Exposition du Système du Monde. This work, far more than a simple exposition, represented a profound and ambitious undertaking, the articulation of a complete, mathematically rigorous account of celestial mechanics. It sought nothing less than to codify the Newtonian revolution, providing a deterministic framework for understanding the universe's structure and evolution. Laplace's central problem, the very core of his endeavour, revolved around the perplexing question of planetary orbit stability. Newtonian gravitational theory, while brilliantly successful in explaining the fundamental force governing celestial bodies, grappled with the long-term fate of the solar system. The observed, seemingly irregular variations in planetary motions suggested the potential for chaotic interactions, possibly leading to catastrophic events. The existing state of celestial mechanics found itself confronted by a fundamental instability. The Exposition du Système du Monde directly addressed this challenge. Its primary aim was to demonstrate the inherent stability of the solar system, to provide an elegant mathematical proof that the observed planetary motions, despite their complexities, would remain within bounds, allowing the solar system to persist indefinitely. This refutation of instability represented a bold assertion, a theoretical triumph over potential chaos. It affirmed the system's permanence, placing the observed intricacies within a framework of predictable order. This pursuit of solar system stability introduced Laplace's most revolutionary idea, the nebular hypothesis. This theory, presented as the most plausible explanation for the solar system's origin and structure, proposed that the Sun and planets formed from a vast, rotating cloud of gas and dust, a primordial nebula, under the influence of gravity and rotation. This nebula flattened, cooled, and eventually spawned the Sun and planets. This origin story offered a framework for comprehending the solar system's peculiar arrangement. The historical context significantly shaped Laplace's endeavour. The 18th century, bathed in the luminous glow of the Enlightenment, fostered a climate of scientific rationalism and the pursuit of universal laws governing nature. The Enlightenment's emphasis on empirical observation, mathematical modelling, and the rejection of supernatural explanations further propelled the quest for scientific understanding. The French Revolution, although disruptive and chaotic, simultaneously created an environment of scientific patronage, with institutions like the École Polytechnique, the first of its kind, supporting research. Laplace, intimately connected with these developments, benefited from and contributed to this flourishing intellectual environment. The Exposition du Système du Monde was a culmination of prior work. Isaac Newton's Principia Mathematica, published more than a century earlier, laid the foundation for gravitational theory, but left many questions unanswered. The work of Leonhard Euler and Joseph Louis Lagrange had created mathematical tools vital for addressing the complex n-body problem of celestial mechanics. Laplace built upon these predecessors, synthesizing Newtonian physics with the advanced mathematical techniques of his time. He sought to furnish a complete, consistent mathematical description of celestial motions, moving, crucially, beyond Newton's qualitative descriptions. This was more than rigorous science. It was a statement about the universe itself. Laplace's work envisioned a universe governed solely by physical laws, where the present state of the system completely and deterministically dictated its future. This worldview profoundly influenced subsequent scientific and philosophical thought. In the Exposition, Laplace sought to furnish an elegant solution. He endeavoured to transform Newtonian physics into a concrete foundation. He provided a comprehensive picture of the universe, emphasizing the concept of causality. The mathematical framework underpinning Laplace's Exposition du Système du Monde centers on the application of differential equations to describe gravitational interactions. Laplace embraced calculus, developed by Newton and Leibniz, but significantly advanced by mathematicians like Euler and Lagrange. This gave him a powerful instrument for modelling the motions of celestial bodies. He considered each planet and celestial body as a point mass. The mutual gravitational attraction between these masses then became the foundation for his equations of motion. These equations, formulated as second-order differential equations, accurately specify the position of an object over time, considering its gravitational forces. Solving these equations precisely represents a complex task, the n-body problem, which involves determining the motion of n objects interacting gravitationally, offers a notoriously challenging puzzle. Exact analytical solutions exist exclusively for simple cases, like a system with two bodies. Laplace adeptly navigated this intricate terrain by employing perturbation theory. Perturbation theory constitutes a central element in Laplace's approach. It handles the complicated interactions between multiple celestial bodies. The fundamental idea involves starting with a simplified, solvable system. This usually comprises a dominant gravitational influence, in this case, the Sun, and a single planet orbiting it. Then, applying perturbation theory, one treats the gravitational effects of the other planets as small disturbances. Calculating these perturbations yields approximate solutions to the equations of motion. Laplace meticulously detailed the influence of Jupiter and Saturn on each other's orbits, developing accurate models for these gravitational interactions. By methodically incorporating these perturbations, Laplace improved the accuracy of his models. This refinement allowed him to predict the movements of the planets with unprecedented precision. Laplace's exposition presents specific claims regarding the stability of the solar system. He meticulously analyzed the nearly periodic nature of planetary orbits. He argued that despite the complex interplays between planets, the system does not merely appear stable, but is inherently so. He showed that the perturbations in the orbital elements of planets, while complex, abounded. The implication is the planets' orbits remain within a specific range over long timescales, averting catastrophic collisions or the escape of planets from the solar system. Laplace also investigated the specific resonant relationships within the solar system, pointing out that the periods of the planets were not simply random, but were related. He demonstrated that these resonances, rather than destabilizing the system, actually enhance its stability. This demonstrated that the solar system possesses a complex, self-regulating mechanism. Laplace's work dismissed the need for supernatural intervention, often proposed in his period to maintain the order of the heavens. The nebular hypothesis, a cornerstone of Laplace's cosmological thinking, details the formation of the solar system. The hypothesis posits that the Sun and planets originated from a vast, rotating cloud of gas and dust called the nebula. Laplace proposed that the nebula, initially diffuse and rotating slowly, gradually contracted under its own gravity. As the nebula compressed, its rotation rate increased, following the principle of conservation of angular momentum. This acceleration caused the nebula to flatten into a disk. Centrifugal force, acting outwards, counteracted the inward pull of gravity. This competition resulted in rings of material shedding from the rotating disk, most of the mass concentrated in the center, forming the protostar that became the Sun. These rings eventually coalesced into planets. This model, by providing a naturalistic account of the solar system, avoided divine intervention. It predicted that the planets would orbit the Sun in a plane, as observed. Laplace's exposition also offers several examples derived from the work to explain observed phenomena. One important example is his explanation of the precession of the equinoxes. The equinoxes slowly shift over time, a phenomenon known since antiquity. Laplace showed that this displacement results from the gravitational forces exerted by the Sun and Moon on the Earth's equatorial bulge. By applying his mathematical models, he accurately calculated the rate of precession, providing a quantitative explanation for this long-observed astronomical effect. He used this to validate his broader theory. Laplace's work exerts an enduring influence on scientific thought. His rigorous mathematical approach to celestial mechanics set a standard for the field. His application of perturbation theory laid the groundwork for the future advances in modeling complex dynamical systems. The nebular hypothesis, while modified over time, remains a fundamental concept in cosmology. The idea of a universe governed by consistent physical laws, lacking any interventions, deeply influenced scientific thought. The Exposition shaped the development of modern cosmology and chaos theory. The deterministic worldview, in which the present fully determines the future, created a fertile ground for scientific investigation and sparked profound philosophical debates. The concept of a deterministic universe, as envisioned by Laplace, provided a strong foundation for scientific exploration of the cosmos. The impact of Laplace's work extended beyond the realm of science. His ideas played a pivotal role in philosophical debates. The concept of a completely deterministic universe, which arises from Laplace's ideas, remains a topic of ongoing discussion among philosophers and scientists. His exposition influenced how humanity perceives its place in the cosmos. His work provided a mechanistic model of the universe. It helped solidify science as a powerful tool for understanding the natural world. Thus, Laplace, in his Exposition du Système du Monde, presented a comprehensive and mathematically rigorous understanding of the solar system. The work's lasting influence lies not just in its specific scientific achievements, but in its demonstration of the power of mathematical modeling and its profound impact on the way we perceive and understand the universe. It cemented the idea that the universe follows strict laws, which opened up new avenues for scientific examination and theoretical work. This framework has influenced fields ranging from cosmology to chaos theory. Laplace's legacy offers a monumental contribution. For science and humanities, the Exposition stands as a testament to the power of reason. It demonstrates the capacity of humanity to unravel the mysteries of existence.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.